Now, there are a lot of game trees that we can go through within poker, and we'll see within later examples that they can get really complicated. But I want to start with a simple game that I think is somewhat intuitive to understand. And we're going to look at this simple game called the shove fold game. Now, versions of toy games like this have been explored in other previous poker texts. The Mathematics of Poker by Bill Chen and Jared Enkelman, Heads Up No Limit Hold'em by Will Tipton, and most recently, the Play Optimal Poker books by Andrew Brokus. All of them do an outstanding job of using this and other toy games to demonstrate poker concepts. And my goal here isn't to teach you poker strategy from this game. I just mentioned 3 books that do a wonderful job of that. What's important within these examples, though, is to understand the way in which we can break down the game using a tree format and calculating a solution. Because that's really what a solver is doing. So by going through these examples, albeit at a smaller and more focused scale, you can see conceptually how a solver will calculate a solution for an entire game tree. So as I mentioned here, I'll bring my mouse over so that I can kind of walk through this game. Any poker scenario here can be visualized here in this form of a game tree. And this game tree, as I mentioned here, is called the shove fold game tree. Now in this game, both players start with 10 big blinds. The small blind posts 5.5 big blinds, and the big blind posts a full big blind. And both players are dealt 2 cards from the deck. In this case here, we're going to look at this from the small blind's perspective. So I'm noting the small blind as the hero in this hand, and the big blind is the villain. And the small blind here has the option to shove for its entire 10 big blind stack. So the remaining 9.5 big blinds after it's already posted the half a blind. If the small blind shoves, the big blind can call the remaining 9 big blind stack, or the big blind can fold. So the small blind here has the option to shove for 9.5 big blinds or fold. And if the small blind shoves, the big blind here can either call or fold. And then the board is dealt out if the big blind calls, and the better hand ultimately wins the pot. This tree can be represented by 3 different types of decision points or action points within the hand. First, we have nodes at which the hero makes a decision. So that's represented here by decision point A. So in this case here, in decision point A, the small blind, which is us, has a decision point of do we shove or do we fold? The second action point here is the node at which somebody else controls that node. So this could be an opponent in this case here, where the big blind has the decision to either call or fold versus the shove. If we're looking at multiple streets here, it could also be the situation where we go to a turn card or a river card and nature takes over and we have one of multiple cards that can actually come in the deck. But at either point, these are specific nodes at which we don't have control. Somebody else or nature has control over those additional nodes. And then finally, we have these points at the end here, which are 1, 2, and 3. And those are endpoints which indicate that the hand is over. There's nothing else that can happen here. There's no more choices that can be made. And our goal in this situation here is to calculate the EV at each endpoint and ultimately try to help inform the strategies that are chosen by the small blind and the big blind within this game. And we can actually break this game down by looking at the math within this game, which I'll actually introduce on the next slide. I'll start by diving into endpoints, and let's look at the easy ones first, points 1 and 3, where both players, the situation ends in folds. So we'll start with point 1. At this point here, the small blind folds the hand and forfeits the half a blind to the big blind, and the hand is over. There is no action. So I'm sure at this point, some of you can already guess that if we are looking to understand the EVs of both players at this point in the hand, the EV of the small blind at point 1 is minus 0.5 big blinds, and the EV of the big blind at point 1 is positive 0.5 big blinds. That's because whenever we get to this node, the small blind will always lose the half a blind, and the big blind will always win the half a blind. Point 3 is also a simple endpoint. In this case here, the small blind shoves for the entire stack, So the small blind shoves and the big blind then folds, forfeiting the one blind that the big blind has already has in the pot. So similar to the point above, the small blind now wins the one big blind from the big blind, and the big blind loses the one big blind. So we can come to the conclusion that the EV of the small blind at 0.3 is one big blind, and the EV of the big blind at 0.3 is minus one big blind. Now finally, the last endpoint we have here is 0.2. And then for here, we actually get the showdown. The small blind shoves and the big blind calls. Now we have a formula to represent this. The formula is equal to the overall pot size times how frequently that player actually wins the pot, or their equity in the hand. And then we take that entire value and subtract the money that that player invested, or in this case here, their starting stack, to determine the overall profit. A few points to make with this. First is the last formula here, this formula at 0.2, it's actually the same formula that we can write at any node. So let's just consider that if we using point number 1 as an example here. After the small blind folds, the pot size is 1.5 big blinds. It represents the two blinds, the one big blind from the big blind and the 0.5 big blinds from the small blind. And the big blind always wins the hand here in this spot. So in this case here, the big blind's equity is 100%, yielding 1.5 big blinds for this side of the equation. And then the big blind invested one blind. So by subtracting out the one blind, the big blind's EV here yields out the 0.5 big blinds. The second point we'll make is that EV is relative to a specific reference point. Now, the way I've chosen to measure this is by looking at the overall change in value of the stack throughout the hand. However, I've seen other texts that do something different. So for instance, Tipton here looks at the overall stack size as expectation value. So the way Tipton would measure this, the EV for the small blind at 0.1 here would be 9.5 big blinds. And the big blind here at 0.1 would be 10.5 big blinds. Now the math stays all consistent and works out the same. So as long as you stay consistent with your reference point, you're fine. And finally, the third point I'll make is that we have two additional formulas here, and we can use these to help solve these formulas out if we have to kind of do some simplifications in the math. The first is that the equity of the small blind and the big blind must always add up to 1, or 100% if you prefer that notation. And this is obvious here. One person has to win the hand, and if he or she does, the other person does not. Secondly is that the EV of the small blind and the big blind must add up to 0. Now, poker is a zero-sum game, and especially when there's no rake involved in this toy game, if one person makes money, it has to come from the other player. So the EV at any given endpoint throughout the game for each player is just the inverse of the other. If you were using a different reference point, so Tipton's for example, it would be that the EV of the small blind plus the EV of the big blind would equal the two stack sizes combined. In addition to calculating EV at endpoints, and once we have calculated the EV at endpoints, we can also do so by calculating EV at any individual node. The EV at any node is simply going to be the EV of each branch of that node multiplied by the frequency at which that node is taken. And I'm going to start here by looking at node B before I go to node A. And as you'll see in a minute, the EV of node A is directly tied to the actions at node B. In fact, we're going to have to calculate all of the endpoints first and work our way backwards in a game tree to fully calculate the earlier options. The big blind has two options. The big blind can call the shove, or the big blind can fold. The EV is going to be equal to each of those individual endpoints that we previously calculated times the frequency at which they're actually taken. And it's obvious here to state that the overall expectation value of this node for both players is going to be dependent on how frequently the big blind calls and the big blind folds. So we can write this formula here to say that the expectation value of the small blind at B is going to be equal to the expectation value of the small blind at 0.3 times the frequency at which the big blind folds, plus the expectation of the small blind at 0.2 times the frequency at which the big blind calls. And that's noted here in this formula. Now we already know these first two EVs. The EV of the small blind here at 3 is going to be +1. So this first part of the equation is then simplified down to just 1 times the frequency at which the big blind folds. And then the second part of the equation, this is simplified down into the frequency at which the big blind calls times this EV, which is from the previous slide, the EV at which the big blind calls. So it's based on the equity of the small blind's hands. The big blind is calculated very similarly. So we are also looking at the different endpoints and then the frequency at which the big blind is taking actions of folding and calling. The main difference here is that this first part of the equation now simplifies to negative the frequency at which the big blind folds, because this first EV of 0.3 for the big blind is -1. And then the second part of the equation is going to be based off of the equity of the big blind's hand. Now you'll notice here I have a little star here on the top of this hand for the big blind, and that's because it's the big blind's decision. It's the big blind's action point. And this equation holds for when we're looking at the entire big blind's range. But if we're looking at one individual hand, the big blind now is going to make a decision here as to which option of these, folding or calling, is the best option. And the big blind, if they're rational, should be taking the choice at which they are making the most EV, or I guess losing the least EV in some cases here, by taking one of those two options here. So we can actually simplify this and say the EV for the big blind at point B for an individual hand is going to be the maximum value of folding and losing one big blind, or taking the value of his or her equity in the hand and using this part of the equation and looking at the EV of the big blind at point 2. Now moving back a node to point A, we can do the same thing by looking at point A. And we'll start with the big blind here, and we can say that the EV of the big blind here at point A is going to be equal to the EV of the big blind at point 1 times the frequency at which the small blind folds, plus the EV of the big blind here at node B times the frequency at which the small blind shoves. Again, we know these EVs already from the previous slides and then this previous example here. The EV for the big blind at point A, or point 1 here, is 0.5. So in this case here, the small blind folds, the big blind earns 0.5 big blinds times the frequency at which the small blind folds. And then the second part here, this EV of the big blind at point B is just taking this equation here and plugging that in. So the frequency at which the small blind shoves times this larger portion of the equation here. And again, if we're looking at an individual hand, we can actually then plug this part of the equation in for this. It's essentially saying the same thing. It's just a difference of whether we're looking at the entire range or an individual hand. The small blind, again, calculated the same exact way here. So the small blind here is simplifies down to be -0.5 times the frequency at which the small blind folds, plus this part of the equation here, so the EV of the small blind at B, times the frequency at which the small blind shoves. And also similar to the first example here, this is the small blind's decision. So the small blind is actually going to be making a decision of, should the small blind shove and get to this second decision point, or should the small blind fold and lose the -0.5 big blinds? So we can simplify this by saying that the small blind is going to choose the action at which it's going to earn more, or in this case here, lose less. So the small blind here will choose this action as long as it loses less than 0.5 big blinds, or the EV is higher than that. Now, a couple equations here, which you've probably gathered from this, is that first, the small blind are at this first decision point here, the frequency at which they fold plus the frequency at which they shove, they must equal 100% or 1. Just at the same thing for the second part here at the big blind, the frequency at which the big blind calls plus the frequency at which the big blind folds has to equal 1. Again, we can't go greater than 1, it can't go less than 1. These are the only two choices that either of these players can make, and the frequencies have to add up to 1. Let's take a step further and look at a slightly more complicated example here. And I want to look at this example here called the raise shove game tree. And in this more complicated game tree, both players start with 10 big blinds here again. And just as like before, the small blind posts the 0.5 big blinds, the big blind posts 1 big blind. But in this case here, we're adding one more step. So instead of just shoving, the small blind is actually raising to 2 big blinds. And now the big blind has an option. The big blind can shove for its remaining 9 big blinds, or the big blind can fold. And if the big blind shoves, the small blind will have the final option to call for its remaining 8 big blinds, or the small blind here can fold. So we have multiple options here in this case. And if the small blind calls here in this spot, hands are turned over again and the board is dealt out with the better hand winning the pot. Similar to our prior example, we can then calculate the expectation value at each of the endpoints and each of the nodes to help inform the strategies that are chosen by the small blind and the big blind within this game. So I'll go through this a little bit more quickly here, and we can take a look at this example because we've seen kind of a little bit of how this actually works. So again, the easier examples here. So endpoint 1. The small blind folds, and just like in our first example, the small blind is going to lose 0.5 big blinds and the big blind is going to win 0.5 big blinds. At endpoint number 2, the small blind raises the 2 bigs and the big blind folds. So at this point here, the small blind is going to win 1 big blind and the big blind is going to lose 1 big blind. And then finally here at endpoint 4, in this case, the small blind raises the 2 and then the big blind shoves, and then the small blind folds. So in this case here, the small blind lost 2 big blinds and the big blind is going to win 2 big blinds. And then finally, endpoint number 3, just like in our first example, once we get to showdown, our EV is just going to be equal to our pot size times the equity of that player's range minus the amount of money invested. And it's going to end up being the same exact value as the value from the first equation. So now we can actually move forward to calculate nodes. Again, we'll start from the end and work our way backwards. So starting with node C, we can see that the EV of the small blind at node C is just going to be the maximum of these 2 values. So the small blind is going to choose, does he or she fold and lose 2 big blinds? Or does the small blind call and take the value from the previous slide and take the equity of his or her hand against the big blind's hand or range? The big blind, we can use our actual formula because it's not the big blind's decision at this point here. The big blind is going to earn 2 blinds when the small blind folds. So the frequency at which the small blind folds times this 2 blinds plus the frequency at which the small blind calls times the overall EV equation using the equity of the big blind's hand versus the small blind range. Working backwards to node B, the small blind here in this spot is going to be based off of how frequently the big blind shoves and how frequently the big blind folds. When the big blind folds, the small blind earns 1 blind because that's the big blind's blind that the big blind posted. So we can simplify the EV at 0.2 here down to 1, and we get the frequency at which the big blind folds plus the frequency at which the big blind shoves times this value here, the EV of the small blind at point C, which we've plugged into this part of the equation. And the big blind is making a decision here to, does the big blind take the maximum value of the big blind EV at point C, which we have up here, or -1 by folding. And then finally, working our way up to node A, the EV of the small blind at node A is going to be the maximum of half a blind, losing half a blind, or the EV of the small blind at point B, which we can then plug in this value. And you see we have kind of a nested max statement here, and that's because the small blind here has 2 decision points here. So the small blind's decision point up here is going to also tie to the small blind's decision point down here. And we can start seeing where the complexity comes into play in a lot of these game trees. Likewise, the big blind at point A is going to be equal to the frequency at which the small blind folds times the EV of the big blind at point 1, plus the frequency at which the small blind raises times the EV of the big blind at point B, which we know that this first EV is equal to 0.5 times the frequency at which the small blind folds, plus this second equation of the big blind here plugged in for the frequency at which the small blind raises here, so times this EV. We have all of our formulas, and I know these are fairly complicated or not so complicated depending on your level of experience with algebra. What these show is how we can actually mathematically calculate expectation values based on the different variables that we have within these examples. But I think it's more tangible if we actually look at an actual example. Let's look at a specific example here where we, as the hero here, hold 7-6 of spades in the small blind. And we want to find the best strategy facing an opponent who's going to shove with this range here. So our opponent has all pocket pairs, ace-2 suited and better, so all suited aces, king-2 suited or better, or so all suited kings, queen-4 suited or better, jack-5 suited or better, 10-8 suited or better, 9-8 suited, ace-2 offsuit and better, so all offsuit aces, king-3 offsuit or better, queen-5 offsuit or better, jack-8 offsuit or better, or 10-9 offsuit. Now this set of hands for our opponent represents 634 combinations, or just under 48% of all of the hand combinations. In this case here, we're saying that the big blind villain shoves in this situation here 47.8% of the time, which means he or she folds 52.2% of the time versus an open, right? And that's based off of the simple math that we have. These values, the frequency at which the big blind shoves, plus the frequency at which the big blind folds, has to equal 1. So once we know how frequently the big blind shoves, we also know how frequently the big blind folds. And we know also by plugging into an equity calculator that the equity of 7-6 of spades against this shoving range, so if the big blind shoves and we happen to call with 7-6 of spades, 7-6 of spades holds 39.6% equity against this range. And what we want to do is we want to actually calculate, well, what's the best strategy a hero should take here, starting at point A, given these exact game conditions. We're going to start by plugging this into our calculation. So we have this formula here to understand, well, what's the expectation value of our small blind here at A with 7-6 of spades? And we start off with this nested max statement. It's based off of the maximum value of the first decision we have here is the maximum value of minus 0.5 big blinds, or this longer equation, which we have another max value here. Now, similar to orders of operations and other math, we actually have to start from the inside and work our way out. So we actually need to calculate this max value before moving on to this max value. And that makes sense, right? We really can't evaluate, in order to calculate this and evaluate maximum values, we'd have to understand and evaluate 0.5 big blinds or minus 0.5 big blinds versus this entire part of the equation. And we don't have that part of the equation yet because we need to actually work through this max first. We know some values here, so we're going to plug in the values that we already know. We know here that our big blind is going to fold 52.2% of the time to this raise, and we know that the big blind is going to shove 47.8% of the time, so we can plug those values in. We also know that the formula here for the expectation of the small blind at 0.3 is going to be equal to the pot size times our overall equity minus the amount we've invested. And in this case here, it's just 20 times the equity of 7-6 of spades, which is 39.6% equity, minus 10. Simplifying this part of the equation first, we can see that this max value here is comparing minus 2 big blinds to minus 2.07 big blinds. So when hero gets to this decision point here, point C, hero has the option to either fold and lose 2 big blinds or call and lose 2.07 big blinds. And as we've already discussed, the hero is going to choose the option at which they earn more EV, or in this case here, they lose less EV. And it's a misconception that I think that a lot of people have, that the solver might choose minus EV plays or worse plays with particular hands to balance out overall ranges. And that's just a false assumption. The solver is always going to choose the maximum EV option for every individual combination against an overall range. And yes, it's in the context of our overall range, but the solver is not going to choose an action that has an inferior EV. And in this case here, we are not going to choose an action, or a rational person is not going to choose an action that has a lesser EV. So we can simplify this part of the equation down to be -2, right? We are always going to choose the folding option here because it is earning more EV than the option of calling and losing 2.07 big blinds. Now we can simplify this part of the equation down. Does the small blind fold and lose -0.5 BBs, or does the small blind lose -0.433 BBs? And what we can see here is that in this case here, losing -0.433 BBs is going to be better than losing -0.5 BBs. When facing a shove from this range, and that's kind of going to the second point here, when facing a shove from this range, hero should always fold to villain shove, because making 2.07 big blinds is less than the alternative of folding, which is losing 2 big blinds. But we also see that raising here yields that overall loss of 0.433 big blinds, which is greater than the folding and losing 0.5 big blinds. So hero here should actually raise with the intentions of folding to a shove, which I know might be a little counterintuitive here, but this is the math of this game, and this is the actual maximum EV way to solve this solution with 7-6 of spades versus this exact range within this exact game. I know this is a very, very, very specific example, but what this example is trying to demonstrate is how these calculations work within the context of an overall game tree, because these calculations make up the foundation for solver algorithms and outputs, and understanding these concepts are critical to using solvers. Now that we've kind of demonstrated how game trees work and how we can actually calculate and work our way through game trees, I'm going to, in the next video, explore solver algorithms and talk to you a little bit about conceptually how solver algorithms work. So I'll see you in the next video and we'll explore that a little bit further.